Okay, so what we're doing is the Coulomb's law today. So our learning goal is to draw similarities in Newton's law of universal gravity. Okay, um, should be a apostrophe there, and the new Coulomb's law for electrical force. Our success criteria, we use vector addition to find the force on a group of charges. All right, so Coulomb's law is the following: K, Q1, Q2, R over R squared. Okay, and just to let you know, this is a vector. All right, so what you're looking at is a vector here. And some similarities and differences between Coulomb's law and the universal gravity is that, well, the universal gravity law, you guys know, is force of gravity is capital G m over r squared. And this is also a force, a vector and a force, actually. So when you're looking at this, you're basically saying to yourself, these have basically the same structure. And that's true, they do. They follow what's called the inverse square law, which I've explained in the past at a couple of different times, okay? And just a quick explanation of the inverse square law is that basically, if I've got, usually things that emanate from a point tend to be sort of following this rule, right? So let's imagine that I've got sort of some sort of, let me try to get that going there. Some sort of thing that emanates from this point. And it goes out a certain distance. We'll call that R. Okay. And the amount of sort of gravitational force that is in this little area here has to be spread throughout this sort of imagine this as like a little sheet of paper that's stretchy paper. Okay. And you can kind of imagine this entire thing as sort of a sphere that emanates out, right? It's a sphere that emanates out, but we're just going to focus on one one little section of the sphere. Okay. Now the inverse square law goes like this. It's like if I double my radius, and so this distance is now 2r, okay? Then if you were to continue this picture outward, you would kind of go out here, you would go out here, you would go out here and here. And if you look at this sort of sheet of paper, it doesn't look like it in my drawing, though it should. Let me make some adjustments on my drawing because it's not good. It's not a good drawing. Let me make a couple of adjustments. Sorry. I'm going to emanate out, all right, like to here. There we go. That's a little better maybe. There, and there. That one should probably go like that. Okay. And now, this is the last. I'm just going to go for it. Now, basically, I've got a sheet of paper that is like this. And if you look closely at this sheet of paper, it's actually 4 times bigger, right? Now, it doesn't look like it in my drawing, but you have to use your imagination. It's 4 times bigger, meaning the same amount of gravitational force here needs to, if it travels out twice as far, it has to cover 4 times as much space. And so it becomes a fourth as intense. It's a 1/4 of intense. So it's less intense by a factor of 4 if you double the distance. So they're inverse. So I'm explaining the inverse square law. Inverse means as the R increases, the force decreases. And the square section, inverse square law, means that if I double my R, then my force of gravity gets diluted by double squared. And if I triple it, it's 9 times or 3 squared, okay? Or it's 9 times as intense, or it's 9 times less intense. And I'll draw this. This is obviously going to be a disaster, but it might actually work. You can kind of see here, well, this one gave me some trouble. If I go out now 3 times further, so this is now R3. Oh, actually, I really messed this up. So R3 should be around right here, or 3R, right? This is 3 times further than this R right here. Then if I draw another sort of little stretchy sheet of paper, in theory, this should be 9 times the sort of area. It's 9. The area in this area right here, this green area, is 9 times this one. So basically, the amount of gravitational force that you had here needs to stretch over 9 times more area. And so therefore, if my R becomes 3 times further, then the intensity of the gravitational force becomes 9 times less intense. And that's just a consequence of geometry, the geometry of a sphere. Okay. Anyway, now that that's all, explained, is the inverse square law. So back to the original question. What are some similarities and differences between Coulomb's law and universal gravity? Well, they both observe the inverse square law, right? Okay. And so there you have it. There's Coulomb's law. And I forgot to even mention what Coulomb's law is. I mean, I think everybody's studied it in Physics 11, but just let me do a quick recap on it. It's essentially the force electrical between 2 charges, right? And my 2 charges are Q and Q, and my distance between the charges is R, just like it's the force gravity between 2 masses with a certain distance, R. Okay, so it's the same exact structure. So so the similarities are they both do observe the inverse square law, and that's obvious by the structure of their equation as well, right? You can kind of say, inverse because one's on the top and one's on the denominator, and the square is because, well, there it is. There's a square there, okay? Let me get rid of some of these markings. All right, so now that that's all sort of discussed, what are some differences? Well, actually, honestly speaking, the only difference between these 2 forces is that these 2 act on charges, and this one acts on masses. And so in order for you to experience an electrical force, you actually have to have a charge. And in order for you to experience a gravitational force, you have to have a mass. And so that's essentially the only thing, right? And so now, under normal circumstances for our basic, physics course, most of our things have a mass, okay? And most of our almost everything has a mass, okay? And so the differences is that the Coulomb's is for charges, and the universal gravity or Newton's law is for masses. Right? So that's pretty self-explanatory as well, I think. So those are some of the differences. Let's just get into an example here. So what are we going to look at? This is maybe a more complicated example. 3 charges have been fixed to the locations in the form of an equilateral triangle of sides 30 centimeters. Okay, the charge of each of the objects is Q. Then we've got a 2Q and a 3Q. Oh, notice they're all pluses, right? Pluses. So what do we know from the previous notes sheet about positive charges? Well, it's up here. Positive charges, what do they do to each other? They repel, okay? So now, basically, what I'm going to do is take this thing, and I'm going to draw a little diagram. Here we go, and there we go. All right. What is the value of electrical force on the smallest charge is the question here. So I'm going to call this guy Q, right? I'm going to call this guy 2Q, and I'm going to call this guy 3Q. If I zoom in on this picture here, we actually have 2 things going on. We've got a downward force, okay? And then we've got a sideways force as well, okay? And so we've got 2 forces acting on this thing. So what I'm going to end up doing is I'm going to end up adding these 2 forces, right, for a total force, okay? A total force. Does that sound like it's a good idea? And so basically that's kind of what we've got. Now, this force here is due to the fact that these 2 objects are positive and they repel each other, okay? This force here is due to the fact that these 2 objects are positive and they repel each other, okay? So knowing the geometry of a equilateral triangle too lets you know that this is at 60 degrees, okay? And then since this and this comes out like this, something called the vertical angle theorem would let me know that, let me get some, maybe just like a red, that this is also 60 degrees, okay? And so basically I've got 2 FEs here, and I need to add them. I need to just add these guys, okay? So they're both called FE at the moment. So that's not a good idea. I want to differentiate these guys a little bit. So I'm going to call one of them just F1, and I'm going to call the other one actually I'm going to call one of them F2, and I'm going to call the other one F3. How's that sound? I'll call this one F3, and I'll call that one F2. And I'm even going to drop the E because in the end, I only have one force going on. I've got only electrical forces here. I don't have gravitational forces. I don't have anything else going on. And so there's no reason to even delineate the fact that it's an electrical force. So basically what I need to do is I need to take F2 and add it to F3. All right. Now, basically, I'm going to write down that F3 is equal to K, 3Q times Q over R squared. And I'm going to put that at 0 degrees. And F2 is equal to K2Q times Q over R squared at negative 60 degrees. You okay with that? And I'm going to kind of just use my vector addition for this. All right. Use my vector addition. I'm going to do this in a bit of a strange way, just to clean up some of this math. By the way, in this case, R is both of these. So R is 30. Where is it? 30 centimeters. You see it right there. Okay. So I'm going to use I'm going to write this down. F2 is 2kq squared over 0.3 squared plus F3 is 3kq. Oh, sorry, I messed up. I didn't. Well, yeah. Let's keep our negative 60 plus 3k q squared over 0.3 squared at 0 degrees. Okay. And believe it or not, you can actually take a look at what I'm going to do here. I'm going to note that I have a k, a q squared, and a negative and a 0.3 squared as a common factor in both of these things. Okay. So I'm actually just going to go ahead and pull that out of there. So I'm going to write k q squared over 0.09. Okay. And this is time 2 at negative 60 plus 3 at 0. Look at that. I got a common factor, pulled it out of there, and I just left the 2 and the 3. So now this whole thingamabob here, this that wasn't a good word. That was a bad word. I'm going to say this whole expression right there is a vector addition. It's a vector addition. And so I'm just going to go ahead and add those guys. Well, how do I add these guys? Well, let me rewrite this. So it's kq squared over 0.09. And then my vector addition, I'll write it in green here. How about that? How does that sound? Do I have a green? Where's my green? Well, I'll write it in blue. It's 2 of sine negative 60 plus 3 at 0 degrees. Oh, sine. Zero degrees. And then it's 2 cosine negative 60 plus 3 cosine 0. Right? And this whole thing is just going to produce, a solution. And then the final solution, I'll go ahead and multiply it by this scalar here. Okay. So this is going to be interesting. And let's see. The sine of 0 is cosine of 0 is 1. And this is 0. So actually, it turns out this is going to be 0. Right? That's going to be 3. I'm going to get the cosine of 60, though. It's the square root of 3 over... All right, so some of these are going to be the square root of 3. So let me just go ahead and get the thing there. All right, so we got that there. You're looking at... so I typed that in. This is a negative 1.7. I typed that in. That's a 4. And then we put them into the Pythagorean theorem. We get 4.34. It turns out that is the this vector here, 4.34. That's the force, okay? And its angle turned out to be negative 23 degrees, all right? Negative 23 degrees, okay? So that's the result of the brackets here, these orange brackets, or the green. It's actually the green. These green brackets here are essentially equal to 4.34 at negative 23 degrees. Okay. And then we still have all of this stuff here. So K Q squared over 0.09. Now that's a scalar, so that just multiplies into the 4.34, okay? And so, as it turns out, we got to, well, what's K, by the way? K, if I remember correctly, is 9 times 10 to the 9. That's a nice one. So there we have it. It's 9 times 10 to the 9. This here is a 9 on the bottom. Which now I'm looking at this down here. That's a 9 times 10 to the negative 2. 10 to the negative 2. If I move it to the top, it's times 10 to the... I'm going to cancel my 9s. Here, I'm going to write this down. 9, oh, I got to write it in. It's 9 times 10 to the 9 times Q squared times 4.34 over 9 times 10 to the negative 2, right? Well, as it turns out, that 9 and that 9 cancel. I've got my negative 2 here, so I'm going to write that up top. Oh, and this is all it at negative 23 degrees. Okay. And so we're going to go ahead and keep going with this. And I've got a 9 times 10 to the 9 and a 9 times 10 to the 2. Sorry, I got a 10 to the 9 and a 10 to the negative 2. And the 10 to the negative 2 moves up to the top, becomes a 10 to the positive 2, giving me 10 to the 11. And so the final result is 4.3 to 4 times 10 to the 11, right? Times Q squared, okay, at negative 23 degrees. And you might say, well, what's Q squared? Well, we don't know what Q is. It depends on what the Q is, right? Basically, this is going to be the force experienced by each of the charges if one of the charges is some value and then the other two are double and triple of that, okay? But at the moment, we don't know, right? We don't know what that is, okay? Anyway, so that's Coulomb's law. This is a little bit more of an advanced question in terms of Coulomb's law is concerned. Take a look at the textbook and some of the sample questions here. Coulomb's law, take a look at some of those, and you can ask me some questions.